be up by Saturday.
Okay.
All right. So, yeah, the first thing we're gonna do is um, write out our chemistry for this. Um, so we know that um, our sodium acetate is going to completely dissociate into water. So we could write out that we have concentration, oops, of CH3, COO minus is equal to 0.3, which we got from this number right here. And we know that our acetic acid has a concentration of 0.5. So CH3, COOH is equal to 0.5. So now that we know our acetate ion and our acetic acid concentration, we kind of rewrite it as A minus and HA. So this is something that we could plug into our Henderson-Hasselbalch equation. So we can do pH is equal to pKa plus log, and then I'll just write A minus over HA. So now this is something we could solve for. So we could do 0.3 divided by 0.5. We'll find the log of that.
4.5.
Yeah, that sounds about right. So yeah, the answer is about 4.5. And yeah, that's applying the Henderson-Hasselbalch equation. So yeah, good job. Any questions on something like this? All right. Cool. So we go ahead and jump to the next slide. So I'm going to clear the screen. So, oh, that's the same thing. The next thing that we're going to go over is titrations. So titrations are a ton of fun. So titrations are basically acid-base chemistry. And based off of what we learned in Gen Chem 1, we know that an acid plus its base plus a base will give us water and a salt. And then some other things that we need to know is the equivalence point is when the concentration of the titrant is equal to the analyte, which is basically fancy talk for what's being added is equal to what's already there. And the equivalence point will be different for different compounds in terms of pH is what I mean by that. So what do I mean by that? So when we add a strong acid with a strong base, the equivalence point is going to have a pH of 7. And we kind of tell that just by thinking it through. So a strong acid plus strong base, both of them are strong, so they'll cancel each other out equally. And then similarly, when we mix a strong base with a strong acid, we'll have an equivalence point of 7. But when we have a weak base being mixed with a strong acid, the equivalence point is going to be less than 7. So we kind of think of it, strong acid will overpower the weak base. So we'll have a pH of less than 7. And then now we have a weak acid paired with a strong base. We kind of use the same logic. If we have a strong base, it'll be a little bit more on the basic side. So a pH of greater than 7. And yeah, so we could do some more math to kind of prove our point there. So we have calculate the pH of a titration of 50 milliliters of acetic acid, and you can start concentration there, when 50 milliliters of 0.2 molar NaOH is added. And then gives us our Ka for acetic acid. So based off of this and these graphs that I showed you guys, what predictions can we make about the pH? I'll give you a hint. We have a weak acid paired with a strong base. So what predictions can we make?
No, the pH would be above normal value then, right? Because it's a weak acid.
Mm-hmm.
If it's a strong acid, it has to be below 7.
pH is 0, less than 7, around 5.
Mm-hmm. Yeah, so we could hypothesize that we're gonna have a little bit more of an acidic solution going on. So yeah, we could do some math to prove it. So I'm gonna make this smaller, and let's jump into it. pH at equivalence point. Oh. Okay. Yeah. I believe this problem is also on page 272. I think this is a typo. 50 of 0.2, 40 of 0. Okay, so this is supposed to be a 40 right here. So let's see. The first thing we're going to want to do is convert everything to moles. So we're going to want to work with moles for this first part. And we can do that by doing 50 milliliters. And then we know that 1,000 milliliters, in this case of acetic acid, will give us 0.2 moles. So that way we can conclude, or we can solve through and say that we have 0.01 moles of acetic acid. Let me change something. Okay. And we can do the same thing for our NaOH. So if we have 40 mLs, we can use the same conversion, 1,000 milliliters of NaOH will give us 0.2 moles. So that way we end up with 0.008 moles of NaOH. So yeah. After we do this, the next thing we're going to want to do is combine the two. So we're doing our acid added to our base. I'm going to go ahead and clear the screen. Or let me see what PowerPoint I have next. Okay, so I'm going to clear the screen. And the next thing we're going to do is have our acid added to our base. So we have CH3COOH plus NaOH yields water and our salt. In this case, NaCH3COO. And now we could do our ice table. So water, we know we don't care about because it's a liquid. It remains constant. NaOH, we had determined we have initially 0.008. And for acetic acid, we said 0.01. And then for sodium acetate, we have initially 0. So we know that the two are going to react, and we notice that we have less of our sodium hydroxide. So that one is going to be our limiting reagent. If they were both equal, then they would both be cut down to 0. But in this case, we can only subtract 0.008. We have to do that to this one as well. And on this side, we have an increase of 0.008. So we're left with 0 of our sodium hydroxide. We have 0.08 of our sodium acetate. And lastly, we have 0.002 moles of our acetic acid. So once we get here, another thing that we could solve for is our concentration of our acetate ion. And that actually, let's do A minus, is also equal to 0.008. Does anybody know how I got this number or want to make a guess? What do you guys think? Why would the concentration be 0.008 for our acetate ion? So I got this number basically by breaking apart our sodium acetate. So it's going to dissolve completely in water. And since it dissolves completely in water, we could do an ice table for it. But we would just see that A minus will end up being 0.008. NaOH is limiting reagent. Yes. So we're going to run out of NaOH before we run out of our acetic acid. Why? Because we have a lesser concentration of it. We have a less amount compared to our acetic acid. So you'll notice we have A minus, and we also have HA. So whenever we have A minus and HA, the first thing you guys should think about is the Henderson-Hasselbalch equation. So we're going to implement that. We know pH is equal to negative log Ka plus the log of A minus over HA. So we go ahead and plug these in, plug in these numbers, and then see what we get. And then we can compare. Oh, but before we do that, keep in mind that these are in moles. So actually it would be not the best to portray it as that. So this is in moles also. And the Henderson-Hasselbalch equation, we have to convert back to molarity. So we could do that by saying this many moles over 0.09 liters will give us a molarity of 0.022. And I got the 0.09 liters, which is basically 90 mLs, by adding 50 mLs and 40 mLs for our final volume. And then likewise, we could do the same here. All this over 0.09 liters. And we get a concentration of 0.089. So now that we have the molarity of each of these compounds, we can now plug into our Henderson-Hasselbalch equation. Yeah, I'll go over that one right there. So we end up with a final answer of our pH being equal to 5.35. And that would be an example of a titration problem. And then we could check with our initial hypothesis of it being acidic, and it checks out. Any questions?
How did you get the 9?
I got the 9 from 50 mLs added to 40 mLs.
Oh, okay.
All right. If there are no questions, we could do another titration problem. All right, I'm gonna go ahead and clear the screen then. And then I'm going to add a blank so we can work on it. All right. So this problem we're going to be going over is on page 275, number 3. So number 3 reads, calculate the pH of a titration made after adding 40 mLs of 0.3 molar NaOH into 40 mLs of 0.2 molar of formic acid. And it gives us our Ka for our formic acid. So we can write down the important things. So we're looking for pH. So pH equals question mark. And we know we have 40 mLs of 0.3 NaOH. And we have 40 mLs of 0.2 formic acid. I'm just going to draw like this. I think it's faster. And that's supposed to be an O. So the first thing we're going to want to do is convert everything to moles. So if we have 40 mLs of NaOH, and we know that for every 1,000 milliliters, we have 0.3 moles of NaOH.
0.012.
0.012. So that would be how many moles we have of NaOH. And then we could do the same for our formic acid. So if we have 40 mLs of formic acid, and we know that for every 1,000, we have 0.2, we can conclude that we have
0.008.
0.008 moles of our formic acid. So now we would just do some acid-base chemistry. So we have NaOH plus, and let me write these things down and clear the screen, give myself a little bit more room. It was 0.012, 0.008. So I'm going to clear the screen real quick. We can write out the chemistry of what's going on. And in this case, I'll write out the formic acid. So we have HCOOH plus NaOH yields water and a salt. In this case, it is NaHCOO. And we can do our ice table for this one. So water, we know we don't care about. And then our initial concentrations of these two, NaOH is 0.012. And our formic acid is 0.008. So, and then over here we have 0. Based off of what we have here, what is our limiting reagent going to be?
HCOOH.
HCOOH will be our limiting reagent. So since it's our limiting reagent, we know we're going to run out of that one first. So we could do minus 0.008 minus 0.008 and plus 0.008. So that once we reach equilibrium, we're going to have no formic acid. We're going to have some NaOH left over. So we have 0.004, I believe. Mm-hmm. 0.004. And then for this one, we'll have 0.008. So now that we have all of this, we can see that we don't really have any HA, but we do have A minus. So because we don't have any HA, we know we can't use the Henderson-Hasselbalch equation. We can't divide by 0. So the only thing we have left to go off of is our NaOH, which we still have some left over from. And we know NaOH is a strong base, so dissociate completely into water, so that we end up with Na plus and OH minus. So we have 0.004 here. Once we reach equilibrium, we're going to have 0.004 of our OH. And since we know our concentration of our hydroxide, we can now solve for POH. So negative log 0.004 over 80.
0.008.
And we're doing that division to convert back to molarity. So 0.004 divided by 0.08. Negative log of that. So we get POH to be equal to, I believe is 1.3. And from there we calculate pH to be about 12.7. And that would be that one all solved through. Any questions? Something like this?
Could you repeat where you got the pH?
Yeah. So we solved for POH, which we determined to be 1.3. Okay, you go ahead, Masa. Have a good one. And then a pH we got from 14 minus 1.3.
Thank you.
So yeah, basically the key takeaway is to convert some moles, do your acid-base chemistry, and from there you could kind of see what you have left over. If you have HA and A minus, then you would know to use the Henderson-Hasselbalch equation. But in any other case, whatever you're left with, in this case it was the NaOH, we could just solve for pH using that right there. All right, cool. I think we have, what time is it? Oh, we still have quite a bit of time. Which leads us to our last point. I'm going to clear the screen. So the last thing we're going to go over, and I think this is my last slide. I have two more. Is polyprotic acids. And what I mean by polyprotic acids is an acid that is capable of giving off more than one hydrogen. So a good example would be H2SO4. When it's fully ionized, we can see it dissociates into H plus, and SO4, 2 minus. So that's what I mean by a polyprotic acid, multiple protons. And what's going to happen is basically we're going to use two different ice tables to determine how much it will protonate. And it goes on to say that typically an acid will protonate with a certain Ka, and then its conjugate base will have a Ka smaller than the original Ka. So H2SO4 Ka is greater than HSO4 minus Ka. So it'll become more resistant to ionization the more protons you remove from it. It's basically a summation of what that says. So I think the best way to learn is just to jump into an example of it. So the example I have here is find the pH of a 0.6 molar carbonic acid solution. And it gives us our first Ka, and it gives us our second Ka. And this is also on page 277, if you want to follow along there. But I'll be doing everything here on the whiteboard. So yeah. The first thing we want to do is create our ice table for our first ionization. So carbonic acid is written as, let me give myself some more space here. All right. So carbonic acid is H2CO3. So you can see that it is in fact a polyprotic acid. So the first thing we're going to do is write out what happens when it ionizes. So we have H2CO3 turns into, when added to water, turns into HCO3 minus and H3O plus. And we can do our ice table for this one. So initially we have 1.6, water we don't care about, 0 and 0. And for our change, because it's a weak acid, we're going to do minus x. So since we're doing minus x there, over here we're going to have plus x. So that once we reach equilibrium, we have 1.6 minus x, x, and x. So now this is where Ka would play a factor. So we could do our first Ka, 4.2 times 10 to the negative 7 is equal to x multiplied by x divided by 1.6 minus x. So the first thing we want to do for this one is figure out whether or not we could use our little shortcut. In this case, we have 10 to the negative 7. So yeah, our shortcut would in fact apply here. So we could erase that, and we could erase this x here. So now we just have to solve for x. So we could do 4.2 times 10 to the negative 7 multiplied by 1.6 equals x squared. And then we could do the square root of this to cancel out the square. And then, yeah, just solve through. In this case, x is equal to 8.2 times 10 to the negative 4. So that's equal to this one right here and this one right here. So we're going to write that down somewhere and then come back to those numbers in a second. So I'm gonna go ahead and clear this screen real quick. So for our next ionization, we know that we're gonna be dealing with whatever's left over of our HCO3 minus. And when that gets added to the water, we're gonna see the ionization into CO3 2 minus and our hydronium H3O plus. So for our initial concentrations of all of these, we know that it is 8.2 times 10 to the negative 4 here, which we got from our previous calculations, and as well as for our hydronium. So we have 8.2 times 10 to the negative 4. And the water we don't care about, and our carbonate we have 0. So we'll just do another ice table. Like I said, basically just 2 ice tables. So we could do minus x, or in this case, it'd be easier to do minus y, so that we don't get confused with x from the previous math. So minus y, plus y, and plus y. So once we reach equilibrium, we have 8.2 times 10. Oh, oops. I don't know what I did. Okay. Times 10 to the negative 4 minus y, and 8.2 times 10 to the negative 4 plus y. So what we have to do now is plug in for our second Ka. So we have 4.8 times 10 to the negative 8 is equal to y times 8.2 times 10 to the negative 4 plus y. All this divided by 8.2 times 10 to the negative 4 minus y. So a whole ton of stuff. So we could check for our shortcut, try to make it a little easier for us. And so it's 10 to the negative 8, so there's not going to be much change. So actually, what we could do is negate the bottom y like we would normally do. But we could actually also exclude this top y because the change will be so negligible. So that's a big help. So cancel out those 2 y's, and now we just have 1 to solve for. So we can multiply both sides by their things, but we actually noticed that we could just cancel out these. So we're left with y equals 4.8 10 to the negative 8. So yeah, we can see that our from here we could just plug in. So our concentration of H3O plus is basically 8.2 times 10 to the negative 4. So we can calculate our pH using this number. We could add y, but because it's so incredibly small, it's not going to make any difference. It's like adding 1 to a million. It's still a million, basically. So we could do pH equal to negative log 0.2 10 to the negative 4. And we end up with a pH of about 3.09. And that would be a polyprotic acid. You'll kind of notice that we didn't really need to do the second ice table because it ionizes so little. But that would be how you do it. If we had a stronger weak acid, then perhaps the second ice table would include a substantial, or not a substantial, but a noteworthy change of protons. So are there any questions? Any questions on anything covered this module? It's kind of a lot. This one is a lengthy one. If there are no questions, then I guess we can go over some problems. Any questions over, actually, are there any questions over anything from the past couple modules? I know your guys' exam is soon, I think. That's what you guys had said. I think it starts from all the way till module 8. So let's go back a couple modules and I'll ask you guys some questions. Try and refresh your guys' mind. All right, I'm going to clear the screen. So let's see. If I were to give you, let me go back to a blank. Oh, and before I forget, as usual, just the homework will just be the evens. So yeah. So let's see, this is from module 8. What is the difference between KC and KP? And you can just shout out the answer as you know it. So KC and KP, what is the difference?
KC. Oh, sorry. No, go ahead. Go. You go. No.
Okay. KC. Oh, sorry. KC depends on concentration and KP in the partial, overall, not the partial, but the, I forgot the name of that thing.
Yeah,
But the thing that it's in ATM.
So that's important. Remember that whenever we're dealing with KP, we must convert to ATM. So if I were to do this equation, N2O4 gas turning into N2 gas and 2O2 gas. If I wrote the KC to be, so it's products over reactants, so O2, N2 over N2O4. Would this be our KC?
No, you have to square the oxygen.
Mm-hmm. So we have
And
to
it could
square
also
the.
be Kp because they're both.
That's true. This would also be representative of our Kp. So yeah, we square the oxygen because of this number right here. Good job. The ATM, that's a good one. So we have to deal in ATMs. Let's see. Let's look at. What else can we look at? Let's jump to the next chapter. So now we're dealing with Q versus K. So I'll write Q, 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 K, K, K. We'll do greater than, equal to, less than. So if Q is greater than K, what change are we going to have to do in order to make them equal? Are we going to do more products, more reactants? Let's say we had, so we're going to need more reactants. So we're going to shift to the left. So I'll just draw an arrow to the left. And then Q equal to K, I kind of gave it away, but this would be ideal. This is equilibrium. So we'll have no change. And Q less than K, we can see that if we have a left arrow, obviously this one is going to be a right arrow. So that's that. Le Chatelier's principle. We're going to brush up on that real quick. So let's say I have a exothermic reaction. And we do A plus B yields C plus D. If I were to take away heat from this system, what effect would it have on the K, or I guess Q? Where would the shift be, is basically what I'm asking. So if I were to lower the heat in an exothermic reaction, would it shift to the left or to the right? Or would there be no change? Right question mark. I don't know. So let's see. Let's think this one through. If we have an exothermic reaction, is heat a product or a reactant? Is heat consumed or released? So it's a product. Heat is being released. So we can kind of pretend that we have another component here, which is heat. So if our product side is going up, which way are we going to shift so that we reach equilibrium once again? So we want to go back to the left to balance out the, oh no, he's going down. Where's my eraser? There we go. He's going down. So if we have a decrease in product, we're gonna have an increase. Wait. No, yeah, we're gonna shift to the right. So we have an increase in product since we're taking some away. But yeah, you were right, and that would go left if he was increased. So yeah, that's temperature. Let's see. In our, I'll give you guys another Le Chatelier's thing. So if we have a thing A yields B plus C, gas, gas, gas. If I were to decrease the volume by 1/2, what would happen? I guess 1/2 doesn't really matter. But if I were to decrease the volume, what would happen? Would we get more product or reactants? More products. Let's see. So a decrease in volume will cause a shift to the side with the least amount of gaseous moles. So which side has the least amount of gaseous moles? The left or the right? So the left. This one only has 1 mole, whereas this one has 2. So we would shift to the left. So we'd have an increase of reactants for this problem. It would shift to the left.
Could you explain that again, please?
Yeah, so if you want to flip to page 229, we have that chart that kind of tells us what's going to happen here. So yeah, so we could read that a change in volume under that category, we can see decreased volume will cause a shift to the side with the least amount of gaseous moles. So looking at all of these, we can see that there is a 1 right here that we don't really write, a 1 right here, and a 1 right here. And all of these are supposed to say G in them, by the way. So here we have 1 gaseous mole. And here we have 1 plus 1 from B and C. So we have 2 gaseous moles. And we know according to the rules it tells us, we're going to shift to the side with the least amount. So you say 1 is less than 2. So we would go to the left.
And like besides the rules, how can we, like if we didn't know the rules, how could we tell the same thing but without knowing?
Yeah, so if I were to draw a jar like this, And let's say we have A in here, we have B, we have C. And we know that B and C come together. So they appear at the same time because of the chemistry. We can kind of think it through. If we were to cut the volume in half, or decrease it by any amount, really. So I'll go ahead and let me erase these. Let's say we cut the volume. We have B, we have A. Because we have less space, we're gonna wanna revert back to something that will take up less space. So B and C will recombine to form A. Since A, we only have one thing bouncing around in there, whereas on the product side, we would have two. That's kind of how I like to think about it, how to visualize it. Yeah.
Okay, yeah, now it makes more sense. Thank you.
Yeah, that's kind of like what's going on behind the scenes from the rules. Yeah. And then the pressure one, we can remember, we only need to remember one of the two for pressure and volume, because we know, in this case, we cut the volume down. And because we're having a lower volume, we're having an increase in pressure. So we can kind of use that logic to switch between the two, so that we know if we have an increase in pressure, we could think decrease volume, and we only have to remember the rules for volume. Let's see. What else can we go over? What is Kw equal to? Anybody know this number off the top of their head? 10 to negative 14. Yeah, so it'd be 1.0 times 10 to negative 14, which simplifies to 10 to negative 14. We could also say Kw equals Ka multiplied by Kb. So that's useful for, if we're given 2, we can solve for the third. What else? Okay, if I were to give you this graph of POH, 7, here we have 14, here we have 0. If we have a substance that falls right here, is it acidic or basic? Dealey says acidic. What about the rest of you guys? What do you guys think? Do you agree? Disagree? Do you think it's neutral? So, what if I told you it was actually basic? So, whenever we're reading tables, it's important to look at the the titles. So, yeah. So because it's POH, the lower the number, the more basic it is. If this was a PH, then you would be right, but we're looking at POH. So that's that. Let's see, what else can we go over? What time is it? Oh, so it's 10:23. So actually it's about that time that we end class. But I guess these last 7 minutes, are there any final questions?